Good evening. It's Bill the engineer from Suffolk here. Now this is getting to be a bit of a habit and very unwelcome too. Now this is a story, one of those products which looks absolutely great on paper, but which in my opinion is completely ruined by lousy design. God damn it, look at this stupid bloody awning. You buy supposedly good quality products from name manufacturers, they let you down, and then you've got to re-engineer them to sort them out. Let me explain. Now the problem I had is common to the owners of many 4x4s, and that is which springs you fit. This is a multi-purpose vehicle. Quite often I use it unladen. On the other hand, I do a hell of a lot of towing, and when I go away on a big trip I load it up both in the back and up on the roof. And if you're using standard springs, when it's heavily laden, you lose your trim, goes nose up, and also when you're driving off-road, you'll find you'll be bottoming out at the back. On the other hand, if you fit heavy-duty springs, the vehicle's far too hard and far too lively when you're unladen. Now to me as an engineer, a very attractive solution seemed to be the use of air helper springs. Now these are airbags which go inside the coil springs. You adjust the pressure according to the load, so you've always got an optimum solution. I looked around and I decided to buy air helper springs from the Airlift company, leading US manufacturers. I think they may even have originated them. And I bought a set from Rimmer Brothers, who were well-known parts retailers here in the UK. I bought the air helper springs back in 2015, although I didn't get around to fitting them for another year, and initially they were great. They massively improved the suspension and I was very satisfied. However, after a couple of years, things started to go wrong. And the only way I can describe it is, well, they looked a bit wonky, particularly at the top. I didn't get round to addressing the problem for another year because I knew it's going to be a big job, but by 2019 they were in serious trouble, so I had to get to the bottom of it. I took them out, and anyone who knows these vehicles knows it's quite a big job. You've got to jack up the vehicle, drop the rear axle, undo the suspension in order to get the coils out. And what did I find? Well, here's one of the top bearing pads. It's in two pieces, and the other one's just a bag of bits. Not good. So what we'll do now is we'll go inside, I'll log onto the computer, and I'll try to explain exactly how they came to fail. And by the way, if any of the designers are out there, I suggest that they should look into. I'm not sure they know a lot about engineering design, and I think they might learn something. So let me explain how this works. We have the coil spring at the rear here, and this goes into the top spring carrier, which is part of the chassis. Inside the coil spring we have the airbag, which is inflated. However, the spring carrier is hollow at the top, and so we need to transfer the load from the airbag into the spring carrier, and this is done by what I'm calling the top bearing pad. So let's look at this diagrammatically, and I'm taking a cross section through the rear suspension. We've got the coil spring here sitting inside the top spring carrier, which is channel shaped up here. We've got the airbag in the middle, and the job of the top bearing pad is to transfer the pressure from the airbag into the top spring carrier, and this is done at these points here where there's a support reaction. Before we go any further, I want to ask a little question. Now I'm going to call this option A. I now remove some material, this centre portion here, and I'm going to call this one option B. Question is option A stronger than option B or vice versa? The answer might surprise you, and I'll come back to this at the end. I want to look at the behaviour of the top bearing pad. Now the function is to transfer the load from the airbag to the spring carrier. Now it's a circular pad, quite thick in proportion to the diameter or the effective span. And as you see, there's a small hole in the middle for the inflation tube. The pad is made out of some sort of plastic or rubbery material. I'm not quite sure what. To simplify the explanation, I want to refer to the case of a beam in bending instead. Now qualitatively, the behaviour is exactly the same as for the circular disc, although the governing equations are of course quite different. Now in the case of a beam, it's conventional to show it with the load being applied on the top and the beam being bent downwards, and this is of course the opposite to what we have with the top bearing pad in the air helpers spring, but don't let that confuse you. Now beams resist the applied load by a combination of bending stresses and shear stresses, and as indicated by the colours here in this stress analysis, the bending stresses are at a maximum near the centre of the span and in the top and bottom fibres of the beam, tapering off to nothing at the supports. Whereas with the shear stresses it's the opposite. They are at a maximum at the support points of the beam and also in the middle section or the neutral axis of the beam. Now the bending stresses act parallel to the axis of the beam. When the beam's bent downwards, we have compressive stresses in the top of the beam and tensile stresses at the bottom. By contrast, the shear stresses act across the face of the beam. Now for most beams like this one, where the span is considerably greater than the depth, the bending stresses are much larger than the shear stresses, and if it's overloaded, it will fail in bending. Now for deep beams where the span to depth ratio is reduced, the shear stresses become more important and can even lead to failure near the supports. I've already indicated that shear stresses act across the end face of the beam, so why have we got failure at 45 degrees as indicated here? The reason is that the shear stresses are always accompanied by coexisting tensile and compressive stresses acting in other directions. Now anyone who studies strength of materials, structures, whatever, will know that this is given by Moore's circle, which I show here. Now on the vertical axis, we've got the shear stress, and at 90 degrees on the diagram, which is actually 45 degrees in real life, we've got the coexisting tensile stress, and it's this stress which causes the failure of the beam. And this is indeed what happens in real life. We have here a deep concrete beam, span to depth about 4:1, and it has failed in shear at the supports along these planes at 45 degrees. Isn't it satisfying when reality bears out what the theory predicts? Now for very deep beams where the span to depth ratio is say 2 or below, things change yet again. We find that both the bending and the shear stresses reduce. So with this deep beam, if we support it here and here, and we load it at the top, the main load bearing mechanism is through these compression zones here, which may be thought of as being internal struts. Now this mechanism is often represented by this simple model, where in the deep beam we've got these internal struts, but they're tied together at bottom through this tensile zone. Now obviously the deeper the beam, the narrower the angle and the lower the required tensile force. And this tends to be a very strong load bearing mechanism. Well, I've been driven inside by the very unpredictable UK summer weather. I can hear the rain beating down outside. So this is where I'll finish the video. Now if you manage to get through my whirlwind course on stress systems and failure modes, you've done very well. And you will now immediately recognise that this is typical of a failure under high shear stress. In fact, it's what we would call a punching shear failure. But there's more to it than that. This performed well for the first 18 to 24 months before it started to fail. Why? Well, the reason is exactly the same as 80 to 90% of premature failures for all load-bearing components. Fatigue. I did incidentally do a lot on fatigue and fracture in my technical series on the failure of axles. So what we need to do now is to go back to the computer and look at this in much greater detail to get to the bottom of why it actually failed.